Hello everybody, this is Mr. Walters, AP Chemistry, and I wanted to do a demonstration to represent the effect of solubility and pH, and also a practical look at Le Chatelier's principle. By the way, how's it going? So here we are, we've got our Pasco probe, pH probe, we have a pH reading. This is magnesium hydroxide, and there's the pH of the magnesium hydroxide solution. I actually add, class has started. You're late. Okay, come on in. Anyway, so here's my magnesium hydroxide, and the first thing I want you to do is write out the equilibrium expression for the solid magnesium hydroxide in solution with its ion. So go ahead and do that. While you're writing that, I also have hydrochloric acid here, HCl in red. I'll put that off to the side. And I am going to add a universal indicator. So let's add a universal indicator, acid-base indicator, to this solution. What color is this going to be when I add the universal indicator? Well, there you go. If you said blue, sorry, can't give you credit because that's pretty blue. So you needed to say pretty blue. Anyway, notice the color. If you recall, these acid-base indicators are going to range in color from red, orange, yellow. Green's going to be approximately neutral, and then as you get in the basic range, you're going to get this pretty blue. Well, let's see here. So you should have magnesium hydroxide written out with its appropriate ions in equilibrium. It's going to be solid magnesium hydroxide. What's going to happen when we add the hydrochloric acid? So we're disrupting equilibrium. We're lowering the OH negative. Let's add some more. There, we get a color change. Keep your eye on it. Oops. Well, again, notice we disrupted the equilibrium. We saw a shift in pH going down, but the magnesium hydroxide, solid, responded to that shift, responded to that shift in lowering of OH minus, and the equilibrium moved to the right, releasing more hydroxide ions, and notice the pH went back up again. So what I wanted to do real quick here was just illustrate this on paper, and then I'm going to get right back to the demonstration just to make sure we have a clean grasp on what's going on. So notice the equilibrium expression here. Notice the approximate pH. There's the KSP expression with the KSP value. So let's add hydrogen ions. As we add hydrogen ions, that's going to react with the hydroxide ions, and that's going to make water. The more hydrogen ions that I add, the lower the concentration of the OH minus becomes. So I'm going to be down here as that concentration decreases. I'm obviously going to get a change in pH. The pH is going to be going down. Well, once I stop adding the acid, so let's say I stop right at that point, whatever pH that happens to be. That could be at 6. It just depends on how much acid that I'm adding. You're going to see in the demonstration this might go all the way down to, I don't know, maybe 4 or 5. But anyway, notice that we're adding acid, and the hydroxide ions are decreasing. Once I stop right at that point, we've disrupted the equilibrium. So this magnesium hydroxide under this set of circumstances here, this is going to shift to the right. And as it shifts to the right, we're going to be releasing more and more magnesium ions, but we're also going to be releasing more and more hydroxide ions. So the more that it shifts to the right, the more hydroxide ions we're going to add. Now, notice this is going to be a new pH. So let's say this new pH is 9.1, let's say. All right. So notice if we go down here, that KSP is a constant value under those temperature conditions, and there it is. Notice, since this has to be constant, we have a new equilibrium situation here. This is a new situation after we've added that acid and then we've had a new concentration of the hydroxide ions. Well, for that to stay constant, we know that this went down. How do we know that? Because of the pH. So this had to have gone up. Notice to keep that KSP constant. Let's get back to the video. Let's add some more. Do it quicker. Let's see what happens now. And there we go. We're putting a stress on the equilibrium by removing OH minus. The magnesium hydroxide shifts to the right to release more hydroxide ions. Now we're back to equilibrium again. This is Le Chatelier's principle. Of course, we are reestablishing a new pH, but people, the KSP value, as long as I have some magnesium hydroxide solid in here, and as long as the temperature has not changed, spit it out again. I better be careful about spitting all these words out because that's not good for that's not good in this current circumstances with viruses. Anyway, here we go again. Again, we're shifting the equilibrium by removing OH minus. The system responds to that reduction in OH minus by dissolving and releasing more hydroxide ions. One more time. As long as there's some solid magnesium hydroxide in this solution, even though the pH has changed, the KSP is the same. KSP is not changed. KSP is only going to change if temperature changes. But again, the key is I have to have some of the solid in here remaining. That's the key. Let's go again. Notice color change, color change, color change. So really start adding some more. Let's take a look. And we're responding to that stress by reestablishing new equilibrium concentrations. So the concentrations are new now, but the KSP value is constant. All right, let's move on. Let's get some more in here. Now I'm really going to do it. Let's see what happens here. And there we go back again. So as I add more and more acid, the amount of solid in here is decreasing. As I add the acid, and this is key, as I add the acid, the magnesium hydroxide becomes more and more soluble, releasing more and more magnesium ions and hydroxide ions. Of course, at some point, all of that magnesium hydroxide is going to be ionized. And then we don't have a KSP situation anymore. Let's try and get to that point. See if that does it. Give it a moment. Give it a moment. Well, I think at this point, There is no more magnesium hydroxide solid in this solution. So at this point, at this approximate pH, notice what we have in the solution now. Notice we have excess amounts of H positive ions, and that's excess amounts relative to the smaller number of hydroxide ions that are present. Of course, what we also have are large amounts of Mg double positive ions. In addition, there's obviously a large amount of solvent in there as well. We have a new pH. You could figure out the hydroxide ion concentration present now. It's going to be much less compared to when we started this. And of course, as that hydroxide ion concentration went down, 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 the H positive ion concentration is now significantly higher. Now you'll also notice that there is no more solid in here. There's no magnesium hydroxide solid. What's floating around in here now? Well, we've got lots of water, obviously, lots of solvent. Now we also have excess amounts of H positive compared to hydroxide based on the pH. We know that. What else is present? Magnesium double positive ions are still present. Again, the solid magnesium hydroxide, that's completely dissolved. This low pH, we have high, I'll say it again, we have high solubility of magnesium hydroxide at this low pH. One more time. High solubility of that magnesium hydroxide if you have a low pH. All right. Now notice here, if you look closely, you can see that you can see much better through this solution now because you don't have any suspended solid anymore. All that suspended solid has been ionized, and a large majority of that OH minus has been neutralized and converted to water, and now of course we have excess H positive here. All right, well, I hope that was useful in helping us understand the concepts of solubility, pH, and Le Chatelier's principle.